Okay, let's finish off the last talk of the afternoon. We're happy to have Nick Earleys from Weizmann Institute. He's going to tell us about minimal kinematics on N0N.
Okay. Well, I'd like to thank the organizers for the invitation to speak here today. It's great to be back here again. So this will be based on two joint works. One with Freddie Cacciazzo, and a second one with Anna Pfister and Bernd Sternfels. Okay, so the general context here is cubic scalar amplitudes. So in 2013, Cacciazzo, Huh, and Yuan came up with like a really powerful formula to compute a wide variety of scattering amplitudes, in particular phi cubed amplitude, which we heard from Lima and Carolina and others in the previous talks. The simplest, so the CHY formula covers a wide variety of different quantum field theories. The simplest one that it allows to compute is the colored ordered cubic scalar amplitude. So it says n point and these, if we put a colored ordered, we put the prefix colored ordered on here, then this has the structure of the associahedron. So after CHY developed their machinery in I think 2017 or so, ABHY, Kani Hamed, Bai, Huh, and Jan, they showed that color ordered n-point phi cubed amplitudes, they can be thought of as like a parametric family of rational functions, which are associated to the space of deformations of a certain polytope. A polytope is the associahedron. Okay, so so here's a sort of picture. We have M moduli space, M0M, and on this moduli space, we have a canonical form. T equals product of the consecutive minors. And on the other hand, we have connection to the kinematic space, which is where all the action happens. Okay, so what you can imagine is the two-dimensional associahedron is, I don't need to remind most of you, but the two-dimensional associahedron is a pentagon. And as we move around in the space of deformations, we may forget certain facets of that polytope. And in general, we want to extend the facets beyond. And the subject of this talk is to consider deformations of the associahedron such that after we delete enough facets, we end up with something which has a unique bounded component. Okay, so in this case, we end up with, we delete these two guys, then for example, we have the unique bounded component is a simplex. Okay, so the situation is we have a have a scattering amplitude defined via CHY or ABHY on the kinematic space. And as we start setting to 0 some of the Mandelstam invariants, as we start restricting to a subspace of the kinematic space, the amplitude will degenerate and in very nice ways. The simplest, and we call, in the case that when we delete enough hyperplanes, there is a unique bounded region. Well, that situation is called minimal kinematics. Or just MK for short. Okay. Okay, so let me begin. What is M0n? Let me recall to make sure we're all on the same page. M0n is the moduli space of n distinct points on the line, the real projective line or complex projective line, modulo the simultaneous action of BGL2. So we can write M0n alternatively as GER0 of 2n modulo torus, where this is the subspace where all Plukers are non-zero. Okay, so minimal kinematics. The ingredients. Ingredients are the kinematic space, again, space of symmetric matrices, zeros on the diagonal, such that rows and columns sum to 0. And we can write it as we'll write R at the end choose 2, such that the sum J equals 1 to n, of Sij equals 0 for all I 1 to n. So Sii equals 0.
They're looking at symmetric matrices.
Symmetric matrices, yes. Sii equals 0, Sij equals Sj. Okay. Now in M0n, using the Grassmannian as the model, we're going to gauge fix. We'll take a chart, following chart where 1, 0, 1, 1, 1, x1, 1, x2, 1, xn minus 3. And the last guy is identified with 0, 1. Ingredients 2. So minimal kinematics. 1, 2, 2, 3. Given this particular gauge fix, a set T in set of all pairs Ij minus the first two, minus the constant 2 by 2 determinant 1, 1, 1, 2. Okay, so we take a subset T of that set. Okay, and the kinematic subspace we can denote it M K subscript T what we do is we set to 0 set to 0 all Sij such that Ij is in the complement of T inside S. Okay, so minimal kinematics. Can I write up there still in the corner?
Yes.
Okay, so minimal kinematics asks the question, for what Sij, for what subspace subsets T does the following hyperplane arrangement have a unique bounded chamber? Product J equals 1 n minus 3 xj times 1 minus xj times the product 1 ij must equal n minus 3 of xi minus xj. Notice that these are exactly all of the minors of this matrix. And I'm going to decorate the exponents. I'm going to put some exponents on there as follows. Here we have an S1j plus 2. Maybe let me put it like this first. Does not equal 0 have, so the hyperplane complement have one bounded component. And I'm going to define phi n to be what happens when we put an exponent here, S1j plus 2, S2j plus 2, and Si plus 2, j plus 2. So we're just building a multi-value function from the minors in the kinematic space. So a related question is, when does d, the logarithmic derivative, d phi n equals 0, have a unique solution? So just calculate the n minus 3 partial derivatives, calculate the number of critical points, and when is that equal to 1? And there's a famous result of Orlik and Terrell that relates these two questions. Yes?
So in that part there, are you assuming Sij to be in this kinematic subspace or a general Sij?
So far general.
Oh, okay. So the part
So far general,
for is not connected.
for what values of Sij, 0 or non-zero, does this have a unique group? So for what yeah.
So just to clarify, it doesn't matter if Sij equals 2 or 3. Just carry.
0 or non-zero. But we'll assume if it's non-zero, we'll assume that it's generic. So yeah, if you take the Sij's to be non-generic, then things could get a little weirder. But so we'll assume them to be generic. Okay. Okay, so now one guess is that we can already recognize the cube in the first two factors. So naive guess, we could just set all the Si plus 2, J plus 2s to 0. And this is the prototypical situation. In some sense, prototype. I plus 2, J plus 2 equals 0. So we get rid of all of the diagonals. And then the unique bounded chamber is a cube, as we can see. in the case n equals 5 in just 1 second. So let's consider case n equals 4. And phi 4 equals x1 s13 times 1 minus x1 s1 to the s23. And the unique critical point, solving d log phi 4 equals 0, and we get x1 equals s1 3 divided by s1 3 plus s2 3. Now, it is not very interesting. This is just the bounded component is a one-dimensional cube, line segment. But if we go to n equals 5, a bit more interesting. At n equals 5, then we get a following situation. Let's see, if that's x1, x2, that, then this guy is s13, s23, s24, s14. But we also have s34. Okay, and so we set s34 to 0, and then we're left with our cube, and we can see that immediately. Now, okay. So the question is, what are the other ways in which this can happen? And that's where it starts to get interesting. Okay, so other ways, other patterns, other subsets T, such that we get a unique bounded chamber and a unique critical point. So we need to introduce two trees. Turns out that there is a nice indexing set here. So a two tree is so two tree is a graph which you can define inductively, starting with a line segment and adding in a point and joining that point with one of the edges in the preceding graph. We start with a line segment, add a point, we get a triangle, choose one of the edges of that triangle, and join a new point to that edge and iterate. So we start with a line segment, 2, 1, 2, 3, and then we have 3 choices for the next case. 2, 3, 4. And in this case, we've joined it along that diagonal edge and so on. Now let me draw in the next one of the knives in the next step for good measure, because well, you need it. 1, 2, 3. 4, 5. Okay, so this is like the first interesting 2 tree. So got it? Okay, so in this case, I want to produce a 2 tree, which corresponds to setting S34 to 0. So I'm going to produce, what I'm going to do is produce a list of triangles. And you can see that, remember our subset T says subset of 1 through n minus 1, excluding the 2 index set 1, 2. Then we set to 0 everything that is not in T. Okay, so here we see that 3, 4 is not in T, and we're And S34 is exactly the guy that we're setting to 0 in the arrangement. So let T equals 1, 2, 5, 1, 2, 3, 1, 2, 4. Then if you take all edges of these triangles, build a big set of edges, you take the complement, then 3, 4 is missing. So we set S34 to 0.
What about 3, 5?
It goes through the set 1 through n minus 1.
But the tree both sides.
Yeah, remember, so our chart in column 5 had just a 1 in it. Right, so that doesn't do anything.
So can you just erase the 5?
Yeah, the 2 tree depends only on that. Yeah, I kind of want to put it back in later when we calculate an amplitude, but I can delete it for now. So the 1, 2, 5 triangle is going to appear in like every 2 tree. Not necessarily for the combinatorics of the minimal kinematic subspace, but necessary when you want to calculate an amplitude.
Thanks.
Yeah.
I'm sorry, I'm confused. At what stage did we lose cyclic invariance? I mean, I know your gauge fixing broke cyclic invariance, but is that gone? I mean, in your notion of minimal kinematics,
Yeah.
why is S3 special compared to any other 2 adjacent?
So we're classifying minimal kinematic subspaces up to permutation. And the amplitudes will not be just cyclically invariant. We're going to be some bigger non-planar things. Okay, thanks. Okay, so I promised, thanks to Thomas's question, it's a good segue to talk about amplitudes associated to these. The amplitude should somehow reflect the structure of the bounded. Yeah.
I'm sorry, but before we go on, I mean, there are other choices here. You could set.
Absolutely.
That's where you're going next?
Yeah, no, there are other choices. This just happens to be the easiest one to.
It's the only one that's like codimension 1.
Well, okay, so we could set.
You could set.
We could get rid of this guy. Then the unique bounded guy would be this triangle.
Yeah.
Secretly, that triangle is a quadrilateral.
Yeah, sure.
Yes, so I want to avoid that. Yeah. All right, so towards amplitudes. And how's my time, by the way?
You've been talking for like 25 minutes or
Perfect.
20 to 20.
Perfect, thanks. Towards amplitudes. So we're gonna define the CHY formula for the cubic scalar amplitude, and then show what that evaluates to on minimal kinematics in these situations. So Pichazzo and Yuan formula. So if we have a 2 tree, well, okay, forget the 2 tree for now. We have an integrand I, and we'll say it's I'll actually say it's the particular factor for now, 1 through n. Remember that was the product of the cyclic minors.
Just, well, can you clarify just what you said briefly? Plain is that there will be a unique region you cannot leave. It is a response for it.
Yes. The 2 trees happen to be the maximal guys.
Maximal.
The unique region will be a cube in the case that's a 2 tree. The unique bounded region will be a cube when the T defines a 2 tree. If it is some other set, if T is
Some other subsets which are not cubes, which also have a unique region.
But that region will not be a cube. It could be a simplex or something with fewer facets.
Interested in these cases?
Sure, sure, it's very interesting. But not in this talk, yeah.
This, some other graphs don't necessarily do trees that.
Yeah, exactly. Okay, so we'll keep in mind this, the CHY formula says M, N, Y, and for the experts, I'm abbreviating a little bit. There should really be a pair in here. I'm just abbreviating for now. Take the sum over all of the critical points of the log of phi n of 1 over the determinant of h. Now let's say that Hessian determinant times I squared. Okay, so we have to solve this big system of equations for generic values of the parameters. Well, it's known that you get n minus 3 factorial critical points, so it's a very big summation. So the Hessian is the matrix, the determinant of the matrix of the second partials of the function phi log of phi n. And then we have to, the guy that does all the work is this I squared. And I squared may be this part-Taylor factor, and maybe it'll be something more general, something non-cyclic. So next, in fact, that's exactly what I want to do next, which is to say what happens when, for a generic 2 tree. So there is a formula which we can use for a generic 2 tree to define the CHY integrand I, thanks to work of Alex and Jake and Freddie and Nima and Yara. So fix a 2 tree T. So we'll say that this is a collection of triangles where I do put in the triangle 1 to n. So 1 to n is there now. So then what we're going to do is we're going to construct all linear extensions, or all cyclic extensions of the set of triangles in the 2 tree. So we'll let I equal the sum over the cyclic extensions, which I'll define right now, of T, alpha in the set of those cyclic extensions, PT of alpha.
Do you choose a cyclic ordering on each triangle?
Yes.
So first,
So each triangle,
independently.
but it doesn't matter in the end. The thing depends only on up to sign on the set of triangles. So exactly. The sum will change, but after you compactify it, there's also a nice formula due to Alex and others. Okay, so let's see. Let me show you what happens at n equals 4. It's not very interesting, but we do have. Let's see. We can say that in n equals 4, t equals 1, 2, 3, and 1, 2, 4. 2 triangles joined on a common edge, and we'll say that they're cyclically oriented forward. So 1, 2, 3 in that cyclic order, and 1, 2, 4 in that cyclic order. So the set of cyclic extensions are 1, 2, 3, 4, and 1, 2, 4, 3. So we take the sum of those two particular factors, and we get negative 1 divided by what is it? 1, 3, 3, 2, 2, 4, 4, 1. So it just happens to be the particular factor for a different cyclic order in this case. Right, so this is PT 1, 2, 3, 4 plus PT 1, 2, 4, 3. So this is actually special. This is actually reflects the U1 decoupling identity. When you shuffle 4 through all of them, you get 0. Okay. So let's see. So yeah, as anticipated, in the case that we have a 2-tree which is built up inductively by joining a new vertex to an existing edge, then we have I'm going to roll a couple of results here into one. First, if T is a 2-tree, then the hyperplane arrangement, which you get by setting all Sij's for ij not in T, then the I'll say MK hyperplane arrangement has a unique critical point. And there's a formula for that critical point. A little bit beyond the scope, but that formula for the critical point, it's yeah, sorry.
Or does it reach the point?
So you sorry, I lumped 2 in item 2 into the unique bounded chamber.
That corresponds to critical point of that function.
Yeah, the critical point will be inside that bounded chamber. Yes. And 2, and we have an explicit formula for the value of that critical point. But what I want to focus on now is the formula for the amplitude. 2 is M n specialized to M AT. So we're taking our formula here, plugging in I, which we get by taking the sum over all cyclic extensions of the triangles, putting that into the CHY formula, and we're setting to 0 all of the Sij's such that I and j is not in T. And what we get is a product sum over 1 critical point, unique critical point, determinant I squared, and this is the product j equals 1 to n minus 3 of some 4-point amplitudes. I'll write it schematically 1 over Sj, 1 over Tj.
So when you say critical point, it's not necessarily minimum, maximum. Critical point is it? Can it be like a saddle point or?
Good question. I mean, yeah, there is an explicit, okay, there's an explicit expression for it as a rational function. Yeah, I guess I'd have to think about the nature of the critical point, but yeah.
Minimum.
Yes, yeah,
And if it's
it should, yeah.
global, maximum.
Yeah.
Like maybe it's like, but
No, I mean, it's highly nonlinear, but,
I mean, not literally, but it's like there's this I squared, so it's
I squared is auxiliary data, which you evaluate I squared on that critical point, on the critical point of log of 5.
the SCM positive or something.
What's that?
Is the SCM positive or something other critical?
Could be either. I mean, yeah. All right. So maybe, yeah, the next thing I'd like to do is that okay. Okay, so back to our example, 1, 2, 5, 1, 2, 3, 1, 2, 4. Then in this case, we can see the cyclic extensions of this very easily. We take the particular factor sum over all permutations of 3, 4, 5. Of alpha. So it's like 1, 2, 3. 1, 2, 3, 5, 4. You can see it just by permutation and variance under permutations of 3, 4, 5. And in that case, I becomes 1, 2 in the numerator and 3, 1, 4, whatever. 4, 5, 2, 3, 2, 4, 2, 5. Okay, well, if you it turns out the amplitude, which you get here by plugging into the CHY formula, before evaluating it, before specializing it to the minimal kinematics, before enforcing minimal kinematics, has a structure of a hexagon. So it looks like the following. It's 2, 3, 5. There's kind of a heuristic which you can use to write down the assignments of the Mendelssohn invariants to the facets. That heuristic is that you take the set of all pairs of guys in the denominator. You want to know, is Sij, can Sij and Skl appear in the same denominator of the amplitude? Can they be adjacent? And you ask, are the two index sets disjoint. So that's the rule that we did there. And so I'll state the amplitude, and then in sake of time, leave it as an exercise to check what happens when we set S34 to 0. Amplitude is 1 divided by S13, S24. All right, S13, S24. So we get that vertex plus 1 divided by S13, S25. Walking around. Plus 1 divided by S25, S14, plus 1 divided by S14, S23, plus 2, 4, 1 divided by S23, S45, plus 1 divided by S15, S24. And now exercises, not difficult, show that if we set S34 equals 0, then this collapses by a partial fraction identity to a product. So what happens is geometrically that these two facets disappear. So this facet disappears, and this facet disappears, and we have a quadrilateral. So yeah, so the main result was that as you can see, these are 4-point amplitudes, and in general, if we construct T as a two-tree, then the amplitude specialized to the MK subspace will be a product of 4-point amplitudes. Let me give you an interesting example of something which is not a two-tree. Yes.
Yeah, that's something that I was trying to ask. So in this theorem, it's like if condition, but with the only like the opposite
Yeah.
utilization
Yeah.
when there's a region.
Yes. So, yes. Yeah. This is. I stated it this way, but yes, it is if and only if.
Oh, so there's if only this
So
theorem?
if let's see, if two-tree. If we, if only, yes.
Okay.
If that is, if we start with the situation with the set T and the set S as indicated, then it is if and only if, yes.
Okay. So if something is not a two trees, then there will be more than one.
If it is not a two-tree, then it may not be maximal in the minimal kinematics regions. Like if you start with a two-tree, and then set additional S's to 0, then you may still have a unique critical point, but it will no longer be maximal in that thing. So there's like, you cannot set fewer. You cannot get a unique bounded component unless you have a two-tree. You can set more and still have a bounded component, but you still need to set that number goes to
Like,
0.
for example, if you consider like construct graph like this, but add a new vertex that connected to something which is not an edge as well.
Yeah, that's where, yes.
In this case, you will have more than one region.
That's a very interesting question. Let me comment on it right now. Yeah. So for example, it's a great opportunity to do that. Maybe let me come over here. So this is this is into the realm of interesting questions that were opened up by our research. So consider the following set of triangles for n equals 6. N equals 6. Take 1, 2, 3, 3, 4, 5, 5, 6, 1, and 2, 4, 6. Definitely not a 2 tree because they intersect only one element at a time, and they do so pairwise. You can say, well, I'm going to set every edge that does not appear in here to 0. Which guys are not in here? I think S14 is not. 2, 5, 3, 6. Let me get the structure here. 1, 2, 3, 4, 5, 6. 1. So those are the triangles. And we're missing 1, 4, 2, 5, and 3, 6. If we set those to 0, we do not get a unique critical point. We get 2 critical points, then there is not a unique bounded chamber, then log of phi 6 has 2 critical points. And moreover, the amplitude, if you calculate the amplitude, it does not become a product of 3 4-point amplitudes yet. It has the structure of a rhombic dodecahedron. You can compute it. What was the interesting thing that can happen here is if you additionally set S23 plus S24 plus S34 equals 0. If you set this new linear combination of S's to 0, then you have a unique critical point. Then log phi 6 has a unique critical point. And the amplitude there is a product of 3 4-point amplitudes. But you can't access it by a 2 tree. So I would like to how much time?
Maybe it's 2 minutes to just finish up. Yeah.
Okay, so let me just comment let me comment briefly on what can happen when we go to higher Grassmannians, right? So M0n is G2n modulo torus. I ask what happens when we consider G0 of Kn mod torus. Well, there's a lot of interesting stuff that can happen here. In work with Freddie, well, we started exploring all kinds of kinematic degenerations of the following potential. N equals the sum of equals the product I j p I j k s I j k. So here p I j k is a 3x3 minor. Here I'm in 3m. Sij are some generalized Mandelstam invariants. There are 3 index tensors, totally off diagonal, and sum to 0 in different ways. So we ask, what are the possible situations in which we can get a unique critical point? Well, the critical point which we found happened to be in the image of a Veronese embedding. So it's in positive configuration space. So we found a unique, we found an MK subspace such that the critical point has the following form: 1x1, x1 squared, 1 xn minus 1. And yeah, so the things I want to, the thing that sort of let me state about the comment about the motivation for the project. The motivation for the project was to get a better grasp of the positive tropical Grassmannian. And if we evaluate the CHY formula on the Park-Taylor integrand, then the result has the structure of the positive tropical Grassmannian. And if you restrict to the minimal kinematic subspace, you can take a projection of the positive tropical Grassmannian. And so you can there's some nice combinatorics of the rays that you can see. Okay, I think I'll stop here.